Hello and namaste everyone. Welcome to lecture 34 of this NPTEL course on stochastic approximation. If you recall, during this week and the next week we are going to discuss motivations and utility of some variants of stochastic approximation algorithms, namely 2 time scale stochastic approximation algorithm and stochastic recursive inclusion, right. So in particular, in the previous two classes we sort of set the stage that motivated the use of 2 time scale stochastic approximation algorithms. So just to give you a quick recap, recall that a single time scale stochastic approximation algorithm is an update rule of the form, so I should perhaps remove this, is an update rule of the form xn plus 1 equals xn plus alpha n times h of xn plus mn plus 1, right. So you have like one variable which you are updating using one step size sequence. So such algorithms are referred to as single time scale stochastic approximation. On the other hand, the general form for a 2 time scale stochastic approximation is as follows. Here you sort of have two different variables that you are updating, right, and the first variable update rule could depend on both xn and yn, and similarly yn's update rule could depend on xn and yn, right. Now this algorithm itself could be viewed as 1 time scale when alpha n and beta n are of the same order. By that I mean, suppose your alpha n and beta n had the relation that your beta n is, let's say, c times alpha n, right. So then you could club these two variables together, that is zn equals xn stacked over yn, right, and then you can see that you can write an update rule for zn based on these two update rules, and that will have a similar form like this, right. So whenever alpha n and beta n are of the same order, right, then even though we may write it this way, that algorithm can still be viewed as a single time scale algorithm. So what makes such an algorithm 2 time scale is the fact that alpha n and beta n, right, they are of different orders, right. In particular, the different choice of orders will imply that either your alpha n over beta n goes to 0 or beta n over alpha n goes to 0. Okay, so either this goes to 0 or the inverse ratio actually goes to 0. So in this case your alpha n decays much faster than beta n. On the other hand, in this scenario your beta n decays much faster than alpha n, right. So in the previous class we said that sometimes the function that we are interested in, whose 0 we are interested in finding, right, may not have the linearity property, which implies that the expectation and certain things need not get reversed, in which case we have to work with 2 time scale algorithms, right. And in today's class what we will do is we will come up with a motivation for working with stochastic recursive inclusions. Is this okay? In particular, to begin with, let's first look at an update rule for single time scale stochastic recursive inclusion, and the same idea can also be extended to discuss 2 time scale stochastic recursive inclusion, right. So the form for single time scale stochastic recursive inclusion is given over here. So observe that here the update rule has the form xn plus 1 equals xn plus some step size alpha n times zn plus mn plus 1. So notice that unlike a single time scale stochastic approximation where we had h of xn, we don't have h of xn here. Instead, right, we have zn, and we will presume that this function h, right, is actually set valued. Set valued meaning for every x that comes as input to h, the output h of x is actually a subset of rd. So this notation over here represents the power set, so which basically implies that for every input x in rd, h of x is actually a subset of rd, right. So in that sense your stochastic recursive inclusion allows us to study set valued dynamics, right. And in today's class we will somehow try to understand why would we want to study set valued dynamics in a very a specific context, right. So coming back to this update rule, okay, here instead of having h of xn, which would have been a vector in a single time scale stochastic approximation, here little h of xn is actually a set valued map. So which means Zn is some d-dimensional vector in h of xn. Is this okay? So whenever you have such an update rule, we will refer to it as a single time scale stochastic recursive inclusion, right. So coming back to this problem that we were interested in solving, that is we wanted to minimize this objective function. Keep in mind that you have the L1 norm over here, right. So I will try to use this objective function again to illustrate why we may want to work with set valued dynamics, right. So let us recall the design of our algorithm, and from there on try to see why we may want to work with set valued dynamics, right. So recall that if you knew expected value of y, right, then and there were no adversaries, right, then we could use this gradient descent algorithm. However, often in practice we do not know expected value of y, instead we have access to samples of y, right, and using these samples of y, right, we want to nevertheless solve this optimization problem, right. So when there are no adversaries, right, this is the update rule that we came up with. For xn plus 1 we came up with this update rule, right, and here notice that we have little yn instead of directly plugging in calligraphic yn. Calligraphic yn recall is an appropriate sample of or I should say calligraphic yn plus 1 is a sample of a suitable coordinate of the vector y, right. In particular in this case it is the sample of y in plus 1. Right. So we do not plug in directly this calligraphic yn plus 1 because, as I said, okay, the expectation of a sign is not the sign of expectation, which holds because this sign function is not a I mean the expectation and sign operators do not interchange with each other, right. So because of that reason, instead of plugging in calligraphic yn plus 1, we actually plug in little yn plus 1, and the idea is that as n becomes larger, right, this yn will start getting closer and closer to expected value of y, right, in which case at least in an asymptotic sense this update rule will start looking like this, okay. So that is the hope. So you can see that in this scenario, okay, estimating your yn on one time scale and using that estimate and plugging it here sort of makes sense, right, because if we had directly plugged in here we would not have managed to have such an update rule. However, by going via this 2 time scale route, okay, at least in an asymptotic sense we are ensuring that this update rule starts mimicking what we would have in the gradient descent case, where recall that gradient descent is the noiseless version of what we want to do, right. Now in some sense I mean please keep in mind that there are no adversaries so far, and I sort of used this recap to recall for you the motivation for working with 2 time scale algorithms, right. And what I will now do is I will sort of tell you how we can rewrite this update rules that sort of enables our analysis, right. So I hope you agree that this update rule over here, okay, which is the xn update rule, can be written in this form, right. So here you can see you have h of xn, right. So I think I should have perhaps used capital H here, okay, because I am going to use capital H for the set valued dynamics henceforth, okay. So presume that capital H is a set valued dynamics here, or as a set valued map, and this is basically capital H goes from RD to 2RD, right. And here when I write little h, I will continue to imply that it is a map from RD to RD, that is when I give x as input to h, the output h of x is also d-dimensional in nature, right. So coming back to our goal, we want to rewrite it in a form that sort of enables our analysis. So I hope you agree that this update rule can be written in this form, where h is given in this fashion. So notice that here what we have done is we have first of all taken the conditional expectation of this expression with respect to in plus 1. So that's why we have 1 over n. Because recall that we had presumed this in plus 1 is being sampled uniformly randomly, right, and on top of that wherever I have yn I have replaced it with expected value of y of I, right. So in some sense this expression matches the gradient of this objective function that we are interested in. Is this okay? Right, and so now epsilon n is basically whatever we have over here, right. So whatever we have over here, right, and subtract it with what we really have, right. So yni is basically what we work with, right. So yni is this expression, and this expression we are going to compare it against this idealized expression, right. So this and this cancel off, so what we are left with is this expression, and this mn plus 1 1, right. So the 1 here denotes that this is the noise sequence associated with this xn update. So this expression is basically what we have in the update rule in reality, right, minus whatever is the expression over here, right. So in this sense you can see that if you add h of xn epsilon n and mn plus 1 mn plus 1 of 1, right, you would indeed get back this expression over here, right. So let us try to understand why have I expressed this update rule in this form, right. So this expression whatever you see over here is like an idealized update. It is the update that we would have used if we had known expected value of y, right. So this is the update that we would have used. Unfortunately we don't know this, instead what we have access to is yn, right. So you can think of this term as a perturbation term that is being added, right. So this is like a perturbation or a bias that is being added because of the fact that we don't know expected value of y, instead we have access only to little yn. But nevertheless, since yn is hoped to go to expected value of y for every I, recall that we don't have adversaries here, hence the hope is that for every I this expression will go to expected value of y of I, right. So in that case the sign of this expression and so I think I should be careful here, this is the sign of this expression, okay, and similarly here also it's the sign of this expression, and maybe I should have a big bracket over here, right. Sorry, I think I made a mistake. What was there before is correct, okay, sorry about that, okay. So this is correct, so this is a scalar, so we look at the sign of this expression, this is a scalar, we look at the sign of this expression, and these ai's are vector. I apologize for that mistake, right. So since yn goes to expected value of y, because we are in the situation where there are no adversaries, one would hope that the sign of this expression also matches the sign of this expression. So I am saying one should also hope, because the sign expression or the sign function is not a continuous function. So sign is a discontinuous function. So even though the argument to these sign functions one would hope and one can provably show that this expression converges to this expression, okay, it is not obvious that the sign of this expression should converge to the sign of this expression. But nevertheless I mean we will soon see how to address this, and we will actually invoke the fact that this yn actually goes to expected value of y to tackle this gap, and we will show that in some sense the effect of epsilon n in the behavior of xn, right, is negligible. So I will sort of quantify what this some sense is and so on and so forth, right, and mn plus 1 is basically what we had here minus its conditional expectation with regards to the information that we have at time n. And in that sense one can see that this expression and this expression, if you take its conditional expectation, right, that conditional expectation will be 0, thereby telling us that this mn plus 1 is actually a martingale difference sequence, right. So this is a nice term, this is in some sense an additional perturbation term that we have not encountered so far, and this h of xn is what we have over here. In some sense this is like the idealized update we would like to have, right. And similarly we can rewrite this yn update, right. So recall that the yn update has this form, so we can rewrite this in the form yn plus 1 equals yn plus beta n times g of yn plus mn plus 1 superscript 2. So the superscript 2 means that this is the noise in the update rule for yn, right, where g of y is basically expected value of y minus y, and this is a vector whose ith coordinate equals whatever we have over here, which is this minus the ith coordinate of this expression, right, in particular at yn, right. So if you see, this expression and this expression will cancel off and we would end up with this. Again one can see that if you take the conditional expectation of this with respect to the information that you have at time n, right, and invoking the fact that both calligraphic yn plus 1 and in plus 1 are generated independently and also independently of each other, using that fact one can see that if you take the conditional expectation of this, then this would again be 0, again telling us that this is a martingale difference sequence, right. So in other words, your yn plus 1 has this update rule where again one can view this g as providing an idealized direction. So idealized direction is basically determined by this expression over here, right. So far we have presumed that there are no adversaries, which implies that whatever is the update rule that we have mentioned over here is what is being done at all values of I, right. Now we want to go to the scenario that we were studying, right, which is when a small subset of these I values are adversarial in nature, which means that let's denote these adversarial indices by calligraphic A. So here I have the complement of this. So for any I in A complement, which means that this index I is now not adversarial, so for such non-adversarial or honest coordinates, indeed the update rule matches what we have over here, right. So the update rule matches what we have over here. However, if I is adversarial in nature, right, then this expression can be arbitrary, because this need not follow this update rule, because the adversary need not do what we are expecting it to do. However, the honest workers will indeed do what we are expecting it to do. So the difference between this and this is that in the honest case, right, we presume that this update rule that we have over here is followed for all I, whereas in the case where we have adversaries, this update rule is only followed by honest workers, and for adversarial coordinates we will presume that this yn of I is some arbitrary value. Is this okay? Alright, so now let us see how we can rewrite this update rule, right. So now we have to keep in mind that your yn of I, okay, for adversarial coordinates need not go to expected value of y of I, right. So what we do now is, while we work with the same update rule as in the non-adversarial case, for our analysis we rewrite it in a certain form. So let us try to understand what is that form. So this is the update rule that we had as before, but now we write it as h of xn yn plus epsilon n plus mn plus 1 of 1, right. So here notice that instead of having h of xn, so observe that here we had h of xn, right, in the non-adversarial case. Now I am presuming that this little h, which is actually having two quantities as input, one is xpen and the other is yn, right. And what is this function? This function, right, again I would like to highlight that when I had begun this lecture I had said that this little h is set valued, but I take back that thing. So this little h basically takes as input two d-dimensional vectors and spits out a d-dimensional vector, and for that set valued map we will use the notation of capital H, right. So what is little h of x comma y here? Well, here observe that I split the sum into two parts. One is I in A complement, where recall A complement means it is the set of indices which are honest or non-adversarial in nature. On the other hand, calligraphic A means adversarial. So since your honest workers are indeed doing what we expect them to do, or the honest coordinates, so I am using the word coordinates and workers interchangeably. So the honest coordinates are indeed doing what we expect them to do. Hence here we have written an expression similar to what we had in the on all honest workers case. So observe that here we have written the idealized update direction, right, but this is only for I in A complement. For I in A we basically write this sign expression based on whatever is the input y that is provided, right. So if y is d-dimensional, you look at I in calligraphic A, right, and for all those i's you write basically this sign expression. So in some sense the adversaries don't affect this part of your update direction, but they can control this part of the update direction, right. So this is the definition of h of xy. Now this epsilon n, as before, it is the difference between what we would what is the idealized update direction when we for the case where we hypothetically know this expected value of y, and the realistic scenario where we know yn, right. So epsilon n is the difference between these two expressions. This matches what we had in the previous noiseless scenario also. However, the key difference is previously this I went from 1 to capital N. Here on the other hand we restrict the values of I to lie in calligraphic A complement. Is this okay? So that is what is this epsilon n, right, and I think I should put a bracket appropriately. So the bracket should be something like this, right. So again right, for since I is in A complement, this is like a measurement obtained at a honest coordinate, right. So this one would expect will go to this, and while the sine function is in some sense discontinuous, we will nevertheless show that because yn goes to expected value of y, the effect of this epsilon n in some sense is negligible. So I will talk about those things later on, right. And this noise term is exactly as before, right. Now if you take the conditional expectation of this with respect to the information that you have at time n, then the only thing that is random here is in plus 1, right, and hence if you take the conditional expectation of this minus this expression, one can see that indeed its conditional expectation will be 0, and hence this will continue to be your martingale difference noise, right. So just to summarize, the difference between the adversarial case and the non-adversarial case is what we view as the idealized update direction, right. So in the noiseless case our idealized update direction was given by this expression, right. On the other hand, in the case where we have a small subset of adversaries, right, the update direction has the idealized update direction is what is given over here, right. So again I would like to highlight that the effect of adversaries in some sense is captured over here, right, and let us try to ponder over it for a few seconds, right. So observe that this is the quantity that the adversary can provide, right, but since this quantity is sitting inside the sign expression, what the adversary at worst can do is flip the sign of this expression, meaning if we had expected value of y of I here, we would have gotten the right sign, right. So right sign is basically whatever is there in the true gradient expression, right. However, since we do not have expected value of y and this coordinate is controlled by an adversary, right, the adversary could flip this sign. So in some sense, because of this presence of sign, right, the impact of the adversary is restricted in the sense that in the worst case scenario the adversary can flip the sign, right. Now I would like to think I would like the reader to think about what would have happened if instead of working with L1 minimization we would have worked with L2 minimization of this Ax minus expected value of y's update rule, right. So then I would like to ask you, what do you think would have been the impact of this adversary, right. And similarly as in the noise non-adversarial case, yn's update can be written in this form. However, one needs to now be careful, right, in the no adversary case, right, yn plus 1 had the following update rule. In other words, if you look at the ith coordinate of this, okay, there exists an update rule where you looked at the ith coordinate of this, and that update rule held for every I. However, in the case where we have adversaries, right, this update rule holds true only for the coordinates I which are non-adversarial in nature, right, and for all other i's, these yn i's can be arbitrary. Is this okay? Alright. Now the question is, okay, we have done some algebra, rewritten things in certain form. Where does the stochastic recursive inclusion or the set valued dynamics kick in, right? So towards that we are going to define a set valued map, right. So I am using this capital H notation to come up with this set valued map. So what is this map? This capital H of x is basically containing all vectors of this form. So notice that when I give x as input to this capital H function, right, the output of this function is not one element or not one vector in RD. Instead, it is a collection of vectors of this form. So what is the special property of this collection? Well, it is of this form, meaning it is some convex combination of AI's where so I shouldn't say convex combination, sorry about that, some combination of these vectors AI, right, where these lambda i's are scalars and AI's are your vectors. So recall that AI transpose was the ith row of your matrix A, right. So this AI that we have over here is the transpose of this vector, right. So this was a row vector and AI is a column vector, right. So we have some combination of these A1 to AN, in particular it is a linear combination, right. So we have a linear combination where lambda 1 to lambda n are scalars, meaning they are some numbers, and these lambda 1 to lambda n should satisfy some properties. In particular, whenever I is not in the set of adversarial coordinates, right, this AI transpose let me state that again. For every I that is not in the set of adversaries and AI transpose x not equals expected value of y of I, right. So if they were equal, then the argument to this sine function would be 0. So let us try to avoid that case for the time being, right. So for every I that is not in the set of adversaries and AI transpose x not equals to expected value of I, for such an I we require that this lambda I equal the sign of this expression, right. Now if this quantity is not 0, which is holds because of this insistence that we have, so this either will be positive or negative. So keep in mind that this is a scalar and AI transpose x is also a scalar. So this is a scalar. So since this is not 0, either it will be positive or negative. If it is positive, the sign expression will output +1, and if this argument is negative, the output of this sign function will be -1. So this lambda I should either be +1 or -1 depending on this expression for every I that is not an adversary and AI transpose x not equals expected value of I, right. And for every other I, this lambda I can be any number between -1 to +1. Is this okay? So in other words, for the i's which satisfy both these conditions, the choice of lambda I is unique, it has to be this, but for every other I, your lambda I can be any number between -1 and +1. So by choosing different values of lambda i's for such i's which do not satisfy this condition, I hope you can see that we can cook up multiple such vectors here, right, and because of these multiple vectors we would end up with a set over here, right. And consequently one can see that, okay, this h x comma y which is one vector, right. So this is an element in RD whereas this is a subset of RD, right. So one can see that for whatever value of x and y we have, right, from the definition of h of x comma y that is given over here, right, one can see that this expression or this output will actually lie in capital H of x, right. So that is something that can be verified, right, and this actually holds because we as I told you, whatever be the value of y, right, this can be some arbitrary sign expression depending on the value of y, but whatever be this value, right, now this sign function can only take values between -1 and +1. In particular, if this quantity is negative, it will take the value -1, and if this quantity is positive, it takes the value +1, and if this is 0, then the sign expression can take any value. Is this okay? So keeping that in mind, and since we allow lambda I to be any value between -1 to +1, one can check that h of xy belongs to capital H of x. Is this okay? So because of the set valued nature of this capital H of x, right, the the dynamics of xn is not determined by a vector valued function, instead it is determined by this set valued function, and consequently the limiting dynamics of xn's update will no longer be determined by a differential equation, instead it will be governed by a set valued generalization of a differential equation, which is a differential inclusion, right, and often I will abbreviate differential inclusion by these two words, two letters di, right. So di stands for differential inclusion. In particular, the limiting differential inclusion that governs the update rule of xn is basically this. Is this okay? So now let us just try to understand what is this set valued dynamics of help, or what help does this provide, right. So as I told you, right, the adversary, right, see this is the update rule, right, but as I told you, when we have adversaries we can reimagine the update rule to be of this form, and we can imagine that this some coordinates of this y are coming from adversaries. In particular, y of I for I in A comes from adversaries. So the adversary can basically do whatever they want, right. So when I am at x, right, your h of xy could take different values depending on what your value of y is, right, and in some sense what we are saying is that wherever we are whenever we are at x, this is the nice part of the update we would like to go. However, this expression is controlled by adversary. Now whatever be the choice of adversary depend on this value of y of i's, this will take some value, right. So either this could be +1, -1, or maybe something between -1 and +1, right. So whatever be this value, right, this h of xy will belong to capital H of x. So in this sense what we are saying is that the adversary can pick a sign function each time we visit x, right, and hence although we are visiting x or visiting the same x at different points in time, the adversary could change the value of y, but whatever the adversary does, it will be an element of this set, right. So in this sense one can see that the set valued dynamics is quite natural in the presence of adversaries. I mean it is also natural in the case of sub differentials and so on and so forth, and the idea of sub differential arises over here because this absolute value or the L1 norm is not differentiable everywhere, okay, and that sort of gives rise to sub differentials when the arguments to this this absolute value that is there in this this expression, right. So when the argument to this norm is actually 0, right, then this expression that we have over here is not actually a derivative but rather it is a sub differential. So the sub differential also gives rise to set valued dynamics, but I would not like to go into those details at this point in time. Is this okay, right. So that is how it is. So now one can ask okay, what is a differential inclusion, in particular what can we say about its solutions and so on, right. Now first let us ask what is a solution of a di, right. A solution of a di is any function of time. So you take t in R, right, t in R and y of t in Rd, right. So, y of t is an element in Rd and you have a map like this, and we require that this mapping be absolutely continuous, right, and for almost all t in R, right, because this is absolutely continuous, one can guarantee that its derivative exists for almost t in or almost all t in R, and for almost all t in R, right, this derivative should satisfy this relation that we given over here, and in addition, okay, this y of t should satisfy some initial condition of this form. So, let me again repeat, any map of this form which is absolutely continuous, which satisfies this differential inclusion relation for almost all t in R and an initial condition like this, will be said to be a solution of such a differential inclusion, right. And I would like to highlight that unlike in the ODE case, where when we insisted that this vector field be Lipschitz continuous, that ensures the uniqueness and existence of solutions. In general, the solutions of a DI for an initial value problem need not be unique, which means that for the same initial condition you could have several y of t trajectories, right, which will pass through this initial condition, but they will be different, right. So, in other words, there could be multiple solutions to this DI, right, and the next question is, okay, if the solutions are not unique, at least can we guarantee the existence of a solution to a DI, and one of the sufficient conditions that guarantees the existence of solutions of the DI is the fact that this function h be Murchoud, right. So, when is a set valued function h Murchoud? Well, it is Murchoud if it satisfies the three properties that is listed over here. In particular, the first property requires that for every x, h of x, which is a set, should be convex and compact. Furthermore, we should have a constant kh, right, which is greater than 0, and for every element z in this set h of x, we require that its norm be upper bounded by this constant kh times 1 plus norm x. Sorry about this, this should be norm x, okay. So, which means that when x is very large, this quantity can be very large, but of course it has to have a linear growth, and when x is very small, like very close to the origin, then we require that this expression be bounded by this constant, right. So, this is like a linear growth condition in terms of x that we insist on on every element z in h of x, and finally we require that this function h be upper semi continuous, right. So, I will sort of give the definition of upper semi continuous in the next class, right, but we also require that this function h be upper semi continuous, okay. So, this brings us to the end of this class. Let me quickly summarize what we did. In the previous two classes, we sort of set the stage for why we need 2-time scale stochastic approximation. In particular, we could have some functions which do not allow interchange of expectation on those functions, right, in particular functions which are not linear, right, and in that case we need this notion of 2-time scale stochastic approximation. On the other hand, today we discussed the motivation for working with set valued dynamics, in particular when we have adversaries and so on and so forth. It is often the case that for a particular input the update direction could lie in a set, right, and when it lies in a set, right, that is what gives rise to set valued dynamics, and such dynamics need to be studied from a stochastic recursive inclusion perspective, and which implies that the limiting dynamics will actually be governed by a differential inclusion, right. And in the last few slides of today's talk, we looked at sufficient conditions that guarantee the existence of solutions of a DI. With that, let me end today's lecture. Until next lecture, goodbye and namaste.